Hello, welcome back again to the digital electronics kind of a reading session today on the topic of this memory units. So let us begin and try to understand what it is memory all about. So section 7.1 introduction. So a memory unit is a device. It is an electronic device to which binary information is transformed for storage and from which information is retrieved when needed for processing. So what does it mean? It means there is a memory unit. So this memory unit is a device, electronic device, in which binary information is transformed. Means some information is there, 1, 0, etc. It is transformed from some external agency to inside this 1, 0. For what purpose? For the storage purpose. And from which now from which information is retrieved. We get information out of that when needed for processing. So what happened? This memory unit is a kind of storage area or a storage space where we keep the information, and as and when it is required, we take it, we retrieve it, we take out. Retrieve is to take out that information. So when data processing takes place, data processing means the operation on the data, like addition, subtraction, some logical operation. So whatever data is given in form of 1, 0, if we are doing some arithmetic manipulation or logical operations, that is called data processing takes place. Information from memory is transferred to selected register. So this is a memory unit. So there is another memory element that is also called register. In that register, some data processing task like addition, subtraction, some logical operations, etc., used to take place. So, but in this register, operations are being taking place. But we need some space where after operation or before operation, data needs to be saved. And that is called memory unit, where we either take the data or save the data. We take the data, do the arithmetic manipulation, and then save back it again. So register is a kind of, register is also a memory element, but not for the storage purpose. It is all temporary storage and then data processing, arithmetic operations. So this is a small difference which I want to point out. So intermediate and final results obtained in the processing unit. Processing unit, what is that processing unit? Here it is a register, are transferred back. This is called here transfer back to stored to be stored in memory. Binary information received from an input device is stored in memory, okay, like this. And information transferred to an output device is taken from the memory. So suppose this is some input device here. It gives some information. This is memory unit and some output unit. Suppose monitor is there where we can watch, where we can see the content of the memory unit. So memory unit is a kind of intermediate unit. So binary information received from an input device is stored in the memory and information transferred to the output device is taken from memory. A memory unit is a collection of cells. So what is that memory unit? Now we can define what is memory unit. Memory unit, by definition, you can say that it is a collection of cells capable of storing a large quantity of binary information. See, register is also able to store the data, but it is not for permanent or large scale. It has some limitation. So this is where little bit difference is there as far as memory unit and uh, registers are concerned. So we are talking about in larger capacity. So it has a capable of or capability of large stories. So this is the memory unit. Now coming on the types. So there are two types of memories that are used in the digital systems. One is called random access memory and another one is called read-only memory. One is RAM and another one is called ROM. RAM, ROM. So RAM, that is called random access memory, stores new information for later use. The process of storing new information into memory is referred to as a memory write operation. So when we, suppose this is memory unit, when we put some information from input device into memory unit, that operation is called a write operation. And retrieving the data to the output, that is called a read operation. So suppose this book is there, something is already written here, I am reading. So that is the read operation, memory read operation. However, if I am writing here like this, so that is called write operation. So putting some information is called a write operation and taking out some information is called read. So inputting is called writing and taking out is called reading operation. So process of transferring the stored memory, stored information out of memory is referred to as the memory read operation. RAM can perform both read and write operations. So now we have two types of memory as we just seen that RAM and ROM. So in RAM, that is called random access memory. In this, both operation you can do, writing and reading. So writing is inside W and reading is outside. So read and write both operation you can do. ROM can perform only the read operation. So there is a ROM, this is a RAM, there is a ROM. So ROM has only facility of reading. It means in ROM already data is there. Only we need to read it like this book. This book is already printed. So that is that I am reading only. So that is called reading, taking out the information. But in this in particular case, you can see I'm writing also with the help of some this can be software. So that is reading and writing. However, certain you may not allow to write here. Okay, not allowed to give some information in this text. Okay, so this means that suitable binary information is already stored inside memory and can be retrieved or read at any time. However, that information cannot be altered by writing. So this in ROM, we cannot change the existing information. In ROM, only we can read. ROM is a programmable logic device, as we have seen in previous classes. The binary information that is stored within such a device is specified in some fashion and then embedded within the hardware in a process is referred to as a programming the devices. The word programming here refers to a hardware procedure which specifies the bits that are inserted into the hardware configuration of the device. ROM is one example of PLD. Other such units are programmable logic array, PLA, that we have seen in that AND array as well as OR array, both are programmable. Another one is called programmable array logic, PAL, in which AND section was programmable, OR section was fixed. And the field programmable gate array, that is the advanced version of your RAM, which includes, I think, also memory element or memory units. Our PLDs like ROM, PLA, PL, both all are sequential. A PLD is an integrated circuit with internal logic gates connected through electronics paths that behave similarly to fuses. In the original state of the device, all the fuses are intact. It's all are connected. Programming the device involves blowing those fuses along the path that must be removed in order to obtain the particular configuration of the desired logic function. In this chapter, we introduce the configuration of PLDs and indicate procedure for their use in the design of digital system. We also present CMOS FPGA, which are configured by downloading a stream of bits into the device to configure transmission gate to establish the internal connectivity required by a specified logic function, combinational or sequential. Now, a typical PLD may have hundreds to millions of gates interconnected through hundreds to thousands of internal paths. In order to show the internal logic diagram of such a device in a concise form, it is necessary to apply a special gate symbology applicable to array logic. So these gates used to have large number of inputs. So and large number of arrays are also there, array of logic gates. So that we have to develop now some more advanced version of symbols. So here figure 7.1 shows the conventional and array logic symbols for a multiple input OR. Instead of having multiple input lines into the gate, we draw a single line entering the gate. The input lines are drawn perpendicular to this single line and are connected to the gate through internal phases. In a similar fashion, we can draw the array logic for an AND gates. This type of graphical representation for the input of gates will be used throughout the chapter in array logic diagram. So let us see, this is a conventional diagram of 4 input OR gate. So here we can see array logic symbol is that. So far as the symbol is concerned, same. However, input we have taken one line and then vertically we have given the connection. So this is equal conventional symbol and array logic symbol. Same way we can go for the AND, exclusive or whatever other gates are there. Now coming on the 7.2, random access memory, that is called RAM. So a memory unit is a collection of storage set, as we have seen, together with associated circuits needed to transfer information into and out of the device. The architecture of memory is such that information can be selectively retrieved from any of its internal location. The time it takes to transfer information to and from any desired random locations is always the same. Hence, the name random access memory means writing as well as reading at any place in the RAM. So that is the same. That is why it can access randomly, not a kind of sequential or some other abbreviated RAM. In contrast, the time required to retrieve information that is stored on magnetic tape depends on the location. Magnetic tape is, earlier we have magnetic tape in which we used to record, sound or music, etc. So in order to get information at particular location of tape, we used to access that location. So it is in a kind of some series way. It is not random. A memory unit is stored binary information in groups of bits called word. So group of bits is called word basically here. Word is what? In this memory units, a memory unit stores binary information in groups. So that group of bits is called word. A word in memory is an entity of bits that move in and out of storage as a unit. So while taking the information from memory unit or writing, it is not individual bits, it is word, and word is a group of bits. A memory word is a group of 1 and zeros and may represent a number, an instruction, or one or more alphanumerical character or any other binary coded information. So these words may represent a number, decimal number, binary number, whatever. It may indicate an instruction or command or alphanumerical characters or any other binary coded information. So this word represents, it is not only a message, it can represent a command or control information. So a group of 8-bit is called byte. A group of 8-bit is called byte, and group of 4-bit is called nibble. Most computer memories use words that are multiple of 8 bits in length. Thus, a 16-bit word contains 2 bytes. A 32-bit word is made up of 4 bytes. The capacity of a memory unit is usually stated as the total number of bytes that the unit can store. So total number of byte. So that is called capacity of a memory unit. So here we can see the block diagram of a memory unit. So in this box here we have k address lines, a read line, write. So basically reading should be out. Reading is out operation and writing is the inside operation, and some and bit data input line and bit data. So these are basically, of course, for enabling is, suppose read is enabled, it means we can get the data at the output lines. When write pin is enabled, it means the data which is available at the n bit data input line will be given to memory unit. And the size of memory unit, we can say 2 to power k words and bit per words. So k address lines and 2 to power k is indicating the word lines. So communication between memory and its environment is achieved through data input and output lines. Address selection. So communication between memory and its environment is achieved through the data input and output lines, as we have seen. Data input, output lines, address selection line here, control lines that specify the direction of transfer. So control lines here, read and write. Okay, reading is outward, writing is the inward. So this way you can say control lines. A block diagram of a memory unit is shown in figure 7.2. The end data input lines provide the information to be stored in the memory, and end data output lines supply the information coming out of the memory. The K address lines specify the particular words choosing among the many available. The two control inputs specify the direction of transfer desired. The write input causes binary data to be transferred into the memory, and read input access binary data to be transferred to the out of memory. Inside the memory, right? Outside is the reading. The memory unit is specified by the number of words it contains and the number of bits in each word. So it can say, like there is a class, in this class there are benches. These benches are the memory location, and on each benches how many students are sitting. So that will give you total capacity. Suppose four lines of these benches are there, and on each bench 2 students are there. So capacity of this room is your 8. Similarly here, capacity of a memory unit is determined. So the address line selects one particular word. Each word in a memory is assigned in an identification number called the address, starting from 0 up to 2 to power k minus 1, where k is the number of address lines. The selection of a specific word inside memory is done by the applying k-bit address to the address line. An internal decoder accepts this address and opens the path needed to select the word specified. Memories vary greatly in size and may range from 1024 words, that is 1K, requiring an address of 10 bits to power 32 words requiring 32 address bits. It is customary to refer to the number of words or byte in the memory with one of the letter K, kilo, M, mega, G, giga. K is equal to 2 to power K, 2 to power 10, M is equal to 2 to power 20, and G is equal to 2 to power 30. Thus, 64K is equal to 2 to power 62 megabyte is equal to 2 to power 21, and 4 gigabyte is equal to 2 to power 32 memory size. Consider, for example, a memory unit with a capacity of 1K watts of 16-bit each. Since 1K is equal to 1024 is equal to 2 to power 10, and 16 bits constitute 2 bytes, we can say that the memory can accommodate 20480, means 2 kilobyte. The figure 7.3 shows possible content of the first 3 and the last 3 words of the memory. So let us see figure 6.3. Yeah, so 7.3. You can see. So binary number, decimal number. So first 3, this is the binary, and last 3, 1021, 1022, 1023. So total is 1024, and each is the 16-bit. So 16 numbers are there, and this is the memory content. Memory content can vary, and these are the address, memory address line. So at the 16-bit address line, and I think memory content is also 62 byte. Figure 7.3 shows possible content of the first 3 and last 3 words of this memory. Each word contains 16 bits that can be divided into 2 bytes. The words are recognized by their decimal address from 0 to 1023. The equivalent binary address consists of 10 bits. The first address is specified. The equivalent binary address consists of 10 bits. So let us see. So this is 10 bits. Let us count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 10 bit, and this memory content is 16 bit, means 2 byte. And this is 10, so 2 to power 10, it means 106, 1024 memory locations. So what shall be the capacity? 1024 multiplied by 16. So that is the size of this memory element. The first address is specified with 10 zeros, and the last address is specified with 10 ones, because 1023 in binary is equal to this number. A word in memory is selected by its binary address. When a word is read or written, the memory operation on all 16 bits as a single unit. So 1K to 16 memory of figure 7.3 has 10 bits in the address and 16 bits in each word. As another example, 64 kilobyte into 10 memory means 10 is the bit word size, that is the data size, and 64K is the address lines. We'll have 16 bits in the addresses. 2 to power 16 is equal to 64, and each word will consist of 10 bits. The number of address bits needed in a memory is dependent on the total number of words that can be stored in the memory and is independent of the number of bits in each word. The number of bits in each address is determined from the relationship 2 to power k greater than or equal to m, where m is the total number of words and k is the number of address bits needed to satisfy the relation. So what we have seen that that's how to determine the size of a memory unit and different operations, read and write operation, and data input lines, and types of memory unit, that is RAM and ROM, PLD classification like PLDs, then symbol of this conventional symbol and array logic symbol. These are the introductory things. So with this, thank you so much for attending this session. See you soon.